Nashville Data Scientist of the Year. He has a lot of other credentials. I think you have a new book coming out by Springer. Yeah, Springer later this summer. Stealth Startup. John, I work for Digital Reasoning as their head of analytics. And he has some background in the financial space. So quite a diverse set. Another thing is NLP. He's helped advise me a bit on this in the past, and it's great to have an expert locally here on NLP. So welcome. Thanks, John, for coming.
Thank you.
One more thing, I just want to thank Tyco Commons. They give us the space for free, so they're a sponsor, and we appreciate them doing that. So.
Yeah, so let's see. Can you guys all hear me?
Yes.
Yeah. First thing first, thank you, Greater Nashville Health Analytics and Data Science for putting this together. Thank you for the food. That was really wonderful. And there is food back there if you're fast enough to get to it. A couple questions before I start. So I'm not the only expert in town. There are plenty of experts. I just want to say that. So by all means, everyone here is an expert in something. And I highly encourage all of you to share among each other because, in fact, that's how we build a community. We share with each other. And I think there's a lot to be offered by people here. First thing first, who here is actually in the data science field? Please raise your hand. Okay. Who here is in the healthcare field? Please raise your hand. Okay. And lastly, who here is in biostatistics?
Who what?
In biostatistics or have a biostat background? Oh, you can leave. Thank you. No, I'm trying to make this so. It was a little bit tough this time because I didn't know, because so many people had signed up, what the breadth of knowledge and experience was. So in order to make this more entertaining to everybody and sort of bring everyone in, please excuse me if I don't dive too deeply in depth. This is actually meant to be slightly more high level so that we can have more people participate. But if you do want to follow up with something much more in depth, whether in natural language processing, in causal reasoning, happy to do that and come back and do that. So let me state that. So before I start, did that work? Yes. Have to mention the disclaimer now that I'm independent. I am in the process of starting a new company. It is in stealth mode, so please don't ask me anything. Eventually when we emerge, I'm happy to talk. Thank you. A roadmap of the talk today. I'm going to provide a brief introduction, sort of what the global trends have been. I'm going to talk about the big data revolution that we are a part of. I'm going to talk a bit about why the need for small data, right? If there's a big data revolution, why am I here to talk about small data? I'm going to talk a little bit about how to deal with small data that invariably I think each of us will have to deal with. And lastly, I'll provide a conclusion and plug for my book. So, all right. So, over the past few years, we have heard time and again about the global trend of big data, right? So, who here thinks that we're not in a big data world? Oh, okay, one. Okay, it's good. Right, so we've been inundated with the word big data. We know that Facebook, Google, everyone has a lot of data on us, right? And up until recently, right, that much big data was not really useful for us. Actually, we've had big data for a long time. But it wasn't until the advent of deep learning that we were able to access that big data and to learn from it. So within the past 4 years, the revolution in deep learning using data science, machine learning, and big data has been astronomical. Part of that is because the advent of cloud. So not only do you have the data, but you have the algorithms, you have the actual capacity to actually run that at scale. And what we've seen is we've seen tremendous growth in anything from self-driving cars to a lot of stuff that digital reasoning has been doing in terms of healthcare. There's been a lot of very interesting applications coming out from deep learning, right? We've heard time and again, and you guys, who knows who made this quote first? Right, we've heard this time and again. Data is the new oil. It drives everything. Without data, nothing goes, and the more data you have, the better. So any idea when this was first stated?
1998.
1998. Close, okay, very good. No, so yeah. Go ahead.
95?
95, right? So homework assignment. Everyone afterwards, please go home and take a look. This actually has been around for a bit. And obviously, for the longest time, we've all said data is the new oil because a particular person who started a Coursera course named Andrew Ng created this fabulous graph and publicized it that showed that with traditional models, the more data you have, it plateaus. But with deep learning, the more data you provide it, the better you do. And if you extrapolate this to an infinite supply of data, you're going to have infinite perfect accuracy. Isn't that great? Right? With Moore's law happening and everything else, we're soon going to get to perfect classification. Who believes that, actually? Right, so here. Homer said it right. But what's wrong with this picture? So those of us who practice data science realize that it's not just having data that means anything. It's having labeled data that means everything, right? You have to train on data. We're still in the supervised learning world. And because of that, we have to label the data. We have to tag it as a positive, a negative, a person, a raccoon, whatever, right? So that in itself is a problem. Why is it a problem? Because labeling data is extremely expensive. What you see here, in fact, are images from a common data set. I believe this is ImageNet, I believe. Could be. Right? And someone has to label all this. You actually have to hire people to do that. Right? That's one. Labeling data is expensive. What's another problem with having labeled data? Massive, large.
It can be wrong. Labeled wrong.
Could be wrong. Annotator disagreement. So you might label it one way, your husband might label it the other way, and you guys will not be able to sleep in the same bedroom at night. So this happens a lot. We find that, in fact, if we give any 5 annotators, the ability to label something, right? By the very nature of human cognition, they're not going to agree with each other. And we have people that disagree with each other. You're not going to have a good labeled data set, right? So these are 2 fundamental problems. We find that, in fact, data annotation is the biggest bottleneck that we face, right? So who disagrees with this statement? Okay, so by nature, converse, everyone agrees with that statement. That's perfect, right? This is a very large data set. It's very common. It's used a lot, right? If you think about a lot of the innovations in terms of deep learning for computer vision, it's been ImageNet. But there are 14 million images in ImageNet, right? There are 20,000 categories, which means that as an annotator, you must label this image into one of 20,000 categories, right? So it took 25, as a conservative estimate, 25 human years to label that data set, right? Which is why Dr. Feifei is so, famous, because she managed to actually wrestle this task of getting this label. Now, for you guys, for business, do you think business can afford to actually label that? No, right? The funny thing is that in the real world, there's actually very little labeled data. If you look at an example of, when I say labeled data, let's say that we're doing image segmentation, right? Someone actually has to sit there and segment in actual images to say, this is a building, this is a car, this is a street lamp, and think about how long that will take, right? And if you have to do that, and then have to train on algorithms that can generalize. If you look at deep learning and say, by definition, if you don't have data in terms of millions of samples, you shouldn't be using deep learning. Think about how difficult that is actually to train a data set in order to actually train something that can segment objects and images, right? NLP is another example. You know how many words there are in the English language, right? And how many possible combinations there are? So if you think that you can build a classifier on 10,000 labeled sentences or words or whatever, got something to tell you. It's not going to happen, actually. So, right? It can happen, but it's not going to happen nearly close enough to actually use in business production. It's something we've learned. Right, so how do we deal with small data? Like, what's the traditional way of dealing with small data? Well, we can do this. One, we can gather more data samples, right? And in the past few years, traditionally, as they say, it's been to, number one, mechanical turking. So who here is not familiar with mechanical turk? All right, so Amazon Mechanical Turk was a service that they provided that allowed you to put a task on Amazon, and you can actually sign up. So people who were staying at home mothers, people from foreign countries could sign up and label different tasks. And they would earn maybe a fraction of a penny for each data sample they did, right? So this actually worked out well for a while. And in fact, ImageNet was actually, a large part of it was done by Mechanical Turk, right? So where Amazon set this up, people from South America, from Far East, other countries, stay-at-home moms actually were able to actually generate some additional income by doing this. But it was not easy. It amounted, I think, they did a study to about $2 an hour of nonstop work, which doesn't really work well in developed country standards, but in a lot of emerging countries, there's actually a decent wage. Right, so that's one. Crowdflower, Figure 8, Appen, they're all the same company actually. So this is another way that people have done this, where you actually farm this out to a private company. They operate a lot like Amazon. They have more flexibility in how you define the task. They can not only say yes or no, or right, green or blue. They can actually say, they can generate examples. We have some experience working with them. So they can actually generate, they can type word answers and so forth. This is another way of actually increasing the data set. Right? The third, and the traditional way that large companies attack it, hire some SMEs, assign some SMEs, and this is a killer. If you think about, for instance, in the medical healthcare domain, if you want to actually label, for instance, radiology exams, you have to hire a radiologist to do that. And they are not cheap, right? If you want to look at medical reports, you need to hire a doctor to do that. And you're either going to get a doctor that really shouldn't have been a doctor, or you're going to get a very expensive doctor. And so what happens is, this is a really expensive way of doing it, right? But nevertheless, these are all, top three ways all involve humans, right? You can also look at synthetic data generation. We use an algorithm to try to generate more data examples. This doesn't really work well for text or images, if you think about it. It can work for numerical data. One of the techniques we can talk briefly about is SMOTE. And who knows what SMOTE is here? Who's familiar with SMOTE methods? I see one hand. Okay, yeah, good. Yeah, so SMOTE is a way for synthetic generation of data, and in particular when you have imbalanced data. So quick example, right? So what SMOTE stands for is synthetic minority oversampling. If you think about an imbalanced data set, right? I've got 1 million Democrats and 10,000 Republicans, for instance, right? And you want to get a good survey. One way of doing that is just generating more samples of Republicans, the minority data set, by oversampling the minority set. And you can actually synthetically generate it. Hate when that happens. So you can synthetically generate by really using a nearest neighbor method to identify samples that are nearest to a fixed number of examples of Republicans. So if you imagine this from a actual standpoint, I've got a region of Democrats, a region of Republicans. I can find people that are close to more Republicans and say they're Republican, and I can sample from them. Right? This is the method for SMOTE. It works fairly well, but you can actually see the problem. Doesn't work for text data. It's really tough. Doesn't really work for image data. What does it mean to apply SMOTE to image data? And lastly, it's, are you cheating? Right? So a traditional machine learning method is to oversample your minority data set. A biostat method is to say, let me tackle this from experimental design. Let me perform matching, for instance, where I'm actually undersampling the larger data set, the oversampled set, overrepresented set. Either way, you're just going to end up with something that either is not representative or a smaller data set. So, as a group here, let's try to tackle this. What else can we do?
Generative adversarial networks. Does that work?
Generative adversarial networks. What do you want to do with that?
Well, train a generator to fabricate your minority class, discriminator. It's something that I haven't implemented, but would be neat.
It's good.
Yeah.
That's really good. Yeah. So, is that okay? That's one way. So we're going to talk about that. He's right. So taking a generative approach using adversarial networks allows you to generate more representative data because you're actually learning the distribution of the actual undersampled class, for instance. Right? What else can we do?
Secondary endpoints.
Secondary endpoints. Okay. I'm not familiar with that.
So if you want to label something yes or no, maybe you can say, well, 80% yes or 20% no.
Oh, yes. So taking a probabilistic approach. Yes, thank you. Yes, that is another way we can do that. What else can we do? I can extend this all whole night, so yeah.
Combined weak classifiers?
You can certainly combine weak classifiers. But let me make a suggestion.
Undersampling, the Tomac links?
We can do lots of things, but let me first make a suggestion. And this is what I tell everyone to do, always. When you encounter a problem, let's take a step back and see if you're attacking the problem the right way. Right? So the very first thing I want people to realize is that not all data is created equal. Right? Let's say we're trying to identify a decision boundary. Right? It turns out that you don't really care those that are very far, any sample that's really far from the decision boundary. If you generate more of those examples, does that really help you? Right? So if we look at this graph, bigger. Anything that's way out on the upper left-hand corner or the lower right-hand corner, those examples are not really going to help you improve your classifier. And the reason is they're in a region of space where you're pretty sure they're positive or negative. Right? So on this figure, it turns out only in the aqua? Yeah, right. Only in the aqua region. So you actually care most about samples that are close to the decision boundary. This is actually a concept that's leveraged by a algorithm known as SVM. Yes. Right? An SVM classifier only looks at the points that are closest to the decision boundary to determine the decision boundary. And if you think about it intuitively, why would I generate samples across the board when all I care about are the generating samples that are close to the decision boundary? Because if I generate enough of them, I have the decision boundary to the right and to the left. Right? This is an important concept. Right? Okay, number one. What does that mean? What does that mean from an image perspective? So let's give a little funny example. I want to train a cat and dog classifier. And I'm going to ask you, of these three images, which ones do you care most about? Like, as a classifier, which one's most useful to train your classifier?
The ones we don't know if they're a cat or dog.
Right, so the one on the first one on the right, on the left, that's an easy dog. That's far into this, away from the decision boundary. We don't even need that. Well, how about the second one? What is that?
Yeah.
Take a vote. Who thinks it's a cat? Raise your hand. Wow, that's it. Who thinks it's a dog? All right, it's a cat. Okay, so third one. Is that a cat or dog? Who thinks it's a cat? Let's not go with the fake news part. Yeah, so it's actually, it is a dog. Okay. Go with an oncology example. Okay. We're trying to identify a classifier that identifies oncology language. Of the 1, 2, and 3, just raise your hand. Who thinks 1 is the most important data sample that we can possibly provide? No one. 2. Who thinks 2 is the most important data sample that we can possibly provide? Okay. Who thinks 3 is the most important? Really? How many? Wait, are there healthcare people here?
Yes, but we're not clinicians.
Oh, sorry. It turns out 2 is the most important. 3 is actually very far from the decision boundary. It identifies there is in fact cancer. So, yep. Right. So again, you don't want the one that's the highest probability, right? It goes a little bit to probabilistic, processes when we talk about. So, okay. So I go back and say, you care most about the points closest to the decision boundary that have highest entropy. So this is nothing new, hopefully. Everyone knows this, right? I see a lot of angry faces. I'm just putting people. Do people disagree, or do people say this is magic or whatever? So, or better yet, chiropractic. So. Okay. So which brings me to the purpose of my talk. I'm here to talk about dealing with small data in machine learning. Because in the end, every problem that we face is actually small data. If there's one lesson that I've learned at Digital Reasoning over the years, is that our clients have lots of data. But every problem they come to us with has been small data. And it's been the annotation part that's the most difficult. Right? And it turns out, we can talk a little bit later, but even if you have the right annotation, even if you have perfect annotation, and just say infinite data, there are many problems that you cannot solve. And we can talk about that a little bit at the end. So let's talk about the first method that I'm going to talk about. So a little bit of a funny story. So, if I've heard this before, my daughter we went to a toy store, and I showed her this thing and said, "This is a tiger," back when she was a little girl. The most amazing thing was, that was the only time she saw this stuffed animal. We didn't buy it. Right? A few weeks later at the zoo, she sees this and she says, "Tiger." Right? So this is very innate for human cognition. The fact that we can look at an object, we can generalize what it is, right? Contextualize it, and we ever see it again once more, we know exactly what it is. If you don't believe me, try it with your kid, try it with your niece, try it with your neighbor's kid. It's really interesting stuff, right? This is a concept known as transfer learning, right? And transfer learning is a very hot field in machine learning right now. Happy to discuss it further, and we can talk about inductive transfer learning, the difference between inductive and transductive. There's many different types, but in this case, it's saying that I'm learning from one task in the same domain and transferring it to another task in the same domain. So I'm identifying cats versus dogs, or I'm identifying, oncology language versus, law, legal language. Okay, so we can go through the math if you like. I see a lot of starry eyes. But I think, who's not familiar with the transfer learning paradigm? Okay, good. All right, so we're all good. So, right. If we take transfer learning, now who's familiar with how to apply transfer learning to images? Okay, yeah, so many of you are, right? There's multiple ways, and we know that deep learning classifiers learn semantic representations. And that's a very interesting concept about semantic image representations. This is a pretty image that shows you basically the concept of encoding an image into its representative parts that are generalized, and you generally successfully have higher and higher representations. I didn't put the standard deep learning classifier on here because you guys have all seen it. I think Colin did a great job with it, and everyone else has done whatever. Right? Where you learn the first layer learns the edges, the second layer learns the shading and the shapes, and it successfully builds up higher. One of the things in the evolution of machine learning now is that it builds up even a lot higher than just the image itself. It builds up to actually understanding concepts. What is this is this not just a shape, but this is a tiger. It builds up to adjoining objects to say, this is a tiger with a cage, right? So you can actually build these representations higher and higher, and that allows you to actually have much better classification. Now, the problem, of course, with semantic representations, image representations, even if we do this, we are just at the level of like an earthworm in terms of cognition. We're so far from humans yet that we're not there yet. But it is actually headed in the right direction. Right. So if we take this to word embeddings, this is where there's been astronomical progress in the past year. Right. So me and my coworkers, two coworkers, we wrote a book on the evolution of natural language processing and everything we could about deep learning natural language processing. And we started that a year ago. So there's been a lot of stuff going on. And we can talk a bit about the most interesting stuff right now. So who's not familiar with word embeddings here? All right, so really brief. Right, the concept of word embeddings is say, I've got a bunch of documents. I need to classify them, let's say. And classification being the big task that everyone does. And how do you do that using machine learning? You start with the documents, you break them down. Start with the corpus, you break down individual documents. You take the document, you break them down into individual sentences. You take the sentences, you break them down into individual words, and then you represent the words in a dense vector formulation. Right? The way you generate these vectors allows you to preserve semantic relationships between the actual vectors themselves. What does that mean? That means that I will have certain words that have vector representation that cluster together. And because of that, I've actually can generalize from beyond words, basically. So, any questions? Right. So this is the simple word-to-vect context. And word-to-vect is what people have been using along with GloVe, but they have a big problem. And the problem is the context that is used to generate word-to-vect vectors is only a few words before and a few words after. It's actually very narrow. And if you write like me and other people, maybe like me at least, or I should be, right? You don't just write context within one sentence. You write them within paragraphs, right? The whole concept of there's context to a document. Right. So it doesn't know this. It will not learn representations that have any context beyond just a few words before and a few words after. Right? So in legal language, you're probably familiar with this. Legal language is extremely long. You can have like one paragraph that's just one sentence. Right? Now, this is a problem for word defect. And it's a problem because if I increase the context window when training word defect, right, I'm going to deal with a lot of sparsity. It's going to be really bad vectors. I'm not going to get the relationship up close. But if I train it up close, I'm going to completely ignore what that clause meant. Right? So it's really fun. So it creates a problem. So what people have really innovated on in the past year, so I'm going to let you guys in on old Bert, Elmo, Elon Fitz secret. Right? So people realized two things. They realized that, and this was a little while ago, so a little while ago, a few years ago, they realized that with word vectors, I can start training what is known as a neural language model. And this is literally something that you have a lot of fun with, because you train on a bunch of corpus, and then you give it a word, and it will complete the next word, and with the two words, predict the third word, so it actually can create and synthesize an entire paragraph. Right? So this has been great. You will be surprised to know that a lot of the news headlines you read is actually generated with this fashion, right? Reuters has been very, very big about using this technique. But the idea here is to say, I understand the relationships of the words, and I can predict the next word. And all this formula tells you is that I take the past window of words, and that window could be infinite or it could be a few, and I can use those and predict the next word with the highest probability. Now, if you think about this, this is one means of capturing context in history, right? Obviously, if I take the context, like word defect sort of uses this for the past, let's say, 5 tokens, or 5 words, right? Word defect, because it cheats, can also use the context of the next 5 words, happens to know that too, right? So, but you can actually do this for multiple terms. You can do this for, the past 5 words, the past 5 words, a word back, 5 words, a word back, so forth. And that concept has led to ELMO, right? And what ELMO stands for is embeddings from language models. So what ELMO does is that it takes individual language models that predict each token, and you can think of, it trains a whole bunch of them using different contexts and back, and then it takes them and it combines them in a linear fashion to create a new embedding. And the advantage of this embedding is that it has a lot more context involved. The other advantage of this, in fact, is that you can actually train this on a huge corpus, and it will capture a lot more of that context. So think of word defect on steroids, right? Is this concept of ELMO, and I can talk a bit more about ELMO. It uses LSTMs, they're bidirectional, so still cheating, it's not causal, it looks front and back, but nevertheless, it gives you a tremendous opportunity to do 2 things. I can now train embeddings that have a lot more context than what you expect, right, from a simple context. And what that means is I can take those embeddings for words and can use them to train a classifier, and I can tune it a little bit, but I will get much better representation. And the big problem, for instance, in NLP space, and even image space, up until now, we've been training everything from scratch, right? Like ImageNet got run through 14 million examples to train from scratch. Like, we don't learn words that way. When we learn a new word, we don't learn it from scratch, right? Using ELMO, we're able to learn new words and classify new words by adjusting those embeddings, but we also have come in with our prior knowledge. And this is the biggest problem with machine learning today. One is that it takes a lot of data, and 2, we don't really incorporate prior knowledge. Well, ELMO allows us to do that. We can train ELMO embeddings on the medical side. We can train it on the legal side. We can train it on the financial term side. And when doing so, we're going to learn information and we learn context within these domains. And that allows us to build better classifiers and better predictors in those domains. Any questions?
John, getting back to your Reuters example, can you give an example or a use case of how they're predicting, how they're applying that prediction model to sentences or words?
Right, so you can actually do this on your own. You can actually grab a headlines data set, and you can actually train a language model on it. And then you can actually start, do you know the concept of ad lib? So in the Mad Libs, sorry. The Mad Libs they have predefined sentences, you just fill the words in, right? But if you actually look at a Mad Lib, they're all the same all the time. We humans don't feel that way, and no matter how you build in basically different permutations of the same templates, it's still going to come out. People recognize it very quickly. This is the same boring stuff. Get a new writer, so forth, whatever. So what Reuters have done is they've actually implemented language models to generate, so that they generate the language. You provide, it will provide the terms, but it will actually be generated by the seeding. And that's very important to know that with language models, with these methods, and also adversarial methods, you have to start with some type of seed in order to do that, right? It could be just random noise, but you have to start with something. It's not, it's not clairvoyant to know where you want to go.
So there's a psychology component as well, understanding your reader and understanding what will grab the attention of your reader as well.
Certainly,
and applying
absolutely.
that to the generated sentence.
Yeah.
Headlines.
So again, for Reuters, what they're looking for is introducing novelty and introducing variation. It's exactly the opposite of what we want from people trying to understand what they're writing, right? So here they're pushing language out. When people are trying to understand what they're writing, you want them to write the same way, at least variations, so you can actually understand it. So, any questions? It's all simple stuff? Yeah. Right. So we go a little bit better, right? Remember, the idea here is to actually provide external context to improve our predictions. So this is actually not new. It's been around a while. But it's the innovation now is actually incorporating this with Elmo and with other embedding. It's the idea that you can actually embed concepts. Now, who here is familiar with RDFs? We don't understand what an RDF is, a triple knowledge graph. Oh, and okay, we got one. So maybe we could say this for another time, but I'll give you the 10-second overview. So it turns out that a lot of our knowledge can be represented in what are known as triples. And what a triple is a noun, verb, object, right? So, for instance, in this case, Jack, is the sister of, Jack is the brother of, Jill, for instance, right? So Jack would be the subject, is the brother of is a relationship, right? Predicate, as they call it, and the verb, and predicate is Jill. You can actually represent lots of knowledge that way. There's a relationship between two entities. If you actually do that, you actually can build a corpus of world knowledge. And there are corpora of world knowledge that do that. DBpedia and lots of other things. Well, you can actually embed these relationships in embeddings. And when you do that, you can actually start to understand that this is not just Jack, but Jack, in fact, is related to Jill. And that will help with classification. We'll skip over the slide. Yeah, people again. Okay. So now you've been introduced to these concepts, contextual embeddings. I ask you guys, did we solve the tiger problem? Is that enough to solve the tiger problem?
No.
Who thinks yes?
You need more than one example, right?
Yeah, you need a lot more examples still, right? No matter how much context you build, right? Remember, context is only things that you've seen before, right? Remember the tiger example. My daughter never saw a tiger before.
But she saw a lot of other animals, so she knew what wasn't a tiger.
She saw a lot of examples, exactly, right? So just so you guys, that's a taste, right? The concept of one-shot learning is the ability to be like the tiger, be able to actually train on just seeing one example. And obviously, you can't treat that one example as a machine learning example. What you need to do is you need to understand the context that's embedded with that one example, right? It has ears, it has fur. It's orange and black and yellow and white, whatever. So, right? So that's the one. A related problem that's actually very actively studied right now is known as zero-shot learning, where I don't even see the example. I don't have an example of it, but I can describe what it is. If I say it looks like a tiger, but it doesn't have stripes, who knows what that is? A lion, right? We all naturally think lion. But how do you teach a computer to do that? And that's the field of zero-shot learning. These are very interesting. Happy to talk about it. It's in the book. So yeah. Right. That's still not enough. And this is the concept of causality, which I think, again, biostat people might be familiar with. But I think that the general machine learning people are completely unfamiliar with right now, which is the concept of causal relationships How do you build causal relationships and causal machine learning? Right, we'll save that for another day because that's a big rabbit hole. So. All right. So this is actually a very interesting insight. The world is not random, right? Now we know that, but a machine does not know that. And the question is, how do you teach an algorithm to know that the world is not random? How do we provide that external insight, right? So another example to tell you how crazy it is. CFAR10 is a very common data set used for training images, image recognition, image classification, right? I think there's 50,000 images, but each one of them, just one of them, is 32 by 32 pixels, which is tiny, right? Except for each pixel, there's 3 color channels, and each color channel can take on one of 256 values, right? The possible permutations of that, if you just do it, simple math, it amounts to a very big number, probably more than the number of stars in the universe. A physicist here would probably tell me I'm wrong. So. Right? So if the world were random, each of those permutations would be equally probable. But that's not the case, because we know that this is not a possible permutation. Right? Okay. In fact, very ironically, you guys probably thought about this. This is an example. Like, how many laws of physics do you need to describe completely the laws of motion? Right? So, I mean, it's like, holy smokes, right? We really might be in an algorithm and just, acting as batteries for some human race or alien race or whatever. So, yeah, so this is very important to realize. The world is not random, and we got to figure out how to capture those relationships, right? Both the relationships that we see and the causal relationships, what causes what. So there's been a lot of work that's been going, and again, I'm not going to jump into it, but talk a little bit briefly about Bayesian networks. Who are familiar with probabilistic networks? Right? Right, so Gaussian processes are one thing, but Bayesian networks are a whole lot of things, because now we're capturing relationships. We're able to discover these, and I think we'll save this for another time, because I think this is actually a very worthwhile talk in depth. So hopefully one of you guys will step up. Do we have any Bayesian network experts here? No? Not yet? Okay, you got homework. So this is actually very useful, and it's actually, Bayesian networks are not causal. This is something that I'm not sure if you guys realize, but we can talk about how they can become causal and capture causal relationships. The last thing, which we talked about from the beginning, was you can always generate examples adversarially. And there's been a lot of work being done in terms of GANs, cyclical GANs, conditional GANs, on how to do that. Right? In the end, the process here is to actually try to learn in an indirect way the underlying distribution to generate the examples, and then to generate them by the standard method of training a classifier to full, a generated full discriminator and cycling back and forth. Right? It's okay, but it doesn't solve our problems. Right? And it's okay, it doesn't realize, it still thinks every data sample is equally important, with some caveats. Here, you start off with samples that are just, it's going to be brute forcing. But as it gets closer and closer, it starts to realize when examples, they're not equally weighted. Because it's the ones that are closest, the ones that most likely the full discriminator that matter the most. And you want to harvest those. All right, so this is about all I wanted to talk about. It's been 36 minutes. People look mighty, mighty tired. So last word, plug for my book. Sorry, have to do that. So again, we just came out with a book called Deep Learning for NLP and Speech Recognition. It is the best 600-page book you could ever buy. So. And it is on Amazon. So it's actually much more in-depth than this talk, and it's on pretty much everything else that I've not talked about. So yeah. So it's actually, I'll put the plug in. So any questions? Yes?
Does it go into CNNs for NLP?
What's that?
CNNs for NLP?
Yes, CNN is LP. It goes into whole transfer learning, goes into the different innovations in terms of memory networks. Anything you can think of, with the exception of Elmo, that's in version 2. But
the application of CNNs for NLP?
Yeah, so this book is actually not just theory. There's actually a very big practice to it. And we provided a bunch of Docker images that actually that have embedded notebooks that demonstrate all the concepts in there. So you can pull them from Docker Hub. So
The face generation website too.
it's a face.
Like where we generate fake faces.
Yeah.
I wish I knew so I could share with everyone. That's actually fun to look at.
The fake faces, yeah.
Yeah.
So don't fall in love with one of those. So yeah. That's it. I just want to say, in a brief talk, hopefully it stimulates your perception. Again, I didn't want to do a super deep dive on any of these, but I'm happy to come back and do a really deep dive on this. So, yeah, thank you. So, questions?
Just for context on the LO embeddings, what does it look like to train an embedding? I mean, because for like a Word to vec, on CPU, it's like an hour or two for all of Wikipedia. What does that same task look like for Elmo?
So right now, it's very prohibitive, right? You're much better off, just like you do with a lot of the NLP trained models, to actually pull it down from somewhere else, or to get yourself access to one of the research programs that allows you to train on behalf of, use leveraging Google's entire cloud. It's not something that you want to do currently. It's very prohibitive currently. With that being said, there's a lot of innovation going around on how to more rapidly train the various embeddings, contextual embeddings. So it is, again, a year ago, we would not be talking about this because it wasn't invented back then. So, other questions? So yeah, so quick question, poll here. Who thought this talk was, start with too high level? That's stupid. Okay. Experimental design question. Okay, who thought this talk was, who wanted more depth in the talk? Okay, who wanted code examples? Oh, okay, we do, that's a mix. Who would rather not have code examples, live code, but sort of videotape code? Like, put a little recorded code to run, so you don't have to wait for it. You just hit.
Sort of like, this is it.
This is it, and it's running at high speed. So yeah.
Let's skip all the 5 hours of processing.
Correct.
No, I want you to debug it in front of you.
Who wants? So I mean, who would like code that's provided sort of after the talk, so that you can go experiment on your own? Does anyone do that? Let's say.
Oh, absolutely.
Okay. All right. So the best it sounds like is not having live code. It's having some code, but provided afterwards. And in terms of content, like this is very broad, right? Are people much more happier with sort of one of these topics and diving deep down, sort of explaining, like how do cyclograms work? Right? Good?
Yeah.
Or how do concept embeddings, how do you train them? How do you use them? How do you build a classifier? Very last question is, are people happy with if I had picked one specific domain and done that on just that domain, is that helpful? Versus sort of more broader.
Well, the cool thing about doing one domain is then you can sort of like look around a little bit. I mean, if you do like everything, it's just sort of like a smattering of everything, and that's,
Yeah.
I mean, sometimes useful, but often not, because it's just sort of like all over the place.
Yeah. It's all over the
I
place.
mean, it's really hard to do, because I mean, it's one of those, how deep is too deep and how wide is too wide.
Yeah. No, again, it depends on the audience.
Yeah, oh, totally.
Because this is a big mixed audience. All right, so that's very helpful. If I ever get a chance to do this again, I'll make sure that it is more in depth. So, thank you guys.